Recently we've been talking quite a bit about the natural log of x, and now we're going to consider a different situation, y equals e to the x. This specific function doesn't fit any of our rules, right? It's not power or product rule or quotient rule, or it's not a trig function, and it's not a natural log function. So let's just examine it in terms of our calculator. If we let y1 equal e to the x in our calculator, and then in y2 graph and derive of e to the x comma x comma x, right? So we're considering the derivative of this. Then what will happen in our table of values is that when x has a value of -4, y1 will have a value of 0.018, and y2 will have a value of 0.018. And hopefully you're already noticing something. If we look at -1, then they'll both be 0.368. If we check 4, they'll both be 54.598. So it looks like, based on just examining some things with our calculator, that the function e to the x and its derivative have the same value. We can actually test this using a technique we talked about previously. So what we'd like to know is something about y equals e to the x, but we don't know how to take its derivative. But if we took the natural log of both sides, then this would be the natural log of y equals the natural log of e to the x. The reason we would do this is we know how to take the derivative of the natural log of y. I'm going to apply a property of logarithms to the right hand side to make this x times the natural log of e. And the natural log of e is just 1, so this is the natural log of y equals x. Now if we use implicit differentiation, the derivative of the natural log of y is 1 over y dy dx. The derivative of x is just 1, and if we multiply both sides by y, we get that dy dx equals y. And remember from the beginning, y equals e to the x. Right? Or, more importantly, the derivative of e to the x is itself. It's a unique function because of that feature. Also, if we're taking the derivative of e to any power, we'll call that power u, then we would just use the chain rule. It's always the function itself, e to the u, times the derivative of whatever u is. And we'll look at quite a number of examples of this. Right, but e to the x is a nice function because of the relationship between its derivative and its integral. So first let's deal with some derivatives. What's the derivative of y equals e to the 5x? Well, the derivative of e to anything is itself times the derivative of the exponent, or just 5e to the 5x. Example number 2. Y equals 4 times e to the 1 minus 2x. Well, again, just by using the chain rule, y prime would equal -8 e to the 1 minus 2x, because 4 times -2, the derivative of the exponent is -8. Let's consider another example. Y equals e to the x squared minus 3x minus 1. Well, the derivative of this is just the thing itself, so e to the x squared minus 3x minus 1 times the derivative of the exponent, in this case 2x minus 3. And I prefer to write the derivative of the exponent in most cases in the front, just because I think it looks more correct, but it wouldn't be wrong to have it after as well, as long as it shows it's the product of the two things. Another example, what is the derivative of y equals 2e to the square root of x? Well, the derivative of e is always itself, so it would be 2e to the square root of x times the derivative of the exponent, in this case 1/2 x to the -1/2. And if I clean this up a bit, we'll have e to the root x over x to the 1/2 power. So there's some examples of taking derivatives involving e. Let's consider some more examples where we'll combine what we've just learned with rules that we have mastered to this point. What's the derivative of y equals e to the x plus 3 quantity squared? Well, by the chain rule, this would be equal to 2 times e to the x plus 3 times the derivative of the inside, which is just e to the x. What about y equals x e to the x? Well, by the product rule, this would be 1 times e to the x plus x times e to the x. And this factors, and sometimes this is useful in terms of having to take second derivatives, into e to the x times x plus 1, or 1 plus x. Right? If I had to take the second derivative, I would want to use this form, because then I can just use the product rule once again. What about y equals the sine of e to the x? Well, this is really just a trig derivative along with the chain rule. This would be the cosine of e to the x times the derivative of the inside, which is just e to the x again. What about y equals e to the sine of x? Well, this is just e to the u, so y prime would be itself e to the sine x times the derivative of the exponent, which is just cosine x. Again, I would encourage you to practice yourself. Let's consider y equals the natural log of x plus e to the x. So the derivative of the natural log is just 1 over the argument, so 1 over x plus e to the x. By the chain rule, we need to take the derivative of the inside, so that would be 1 plus e to the x. And we could even clean this up if we wanted to and write it as e to the x plus 1 over x plus e to the x. Another derivative, let's look at y equals e to the 4x over x. I'm going to use the quotient rule in this case, just because. This is going to be 4 e to the 4x times x minus e to the 4x times 1 all over x squared. And cleaning up the numerator, I'll factor out e to the 4x, so this will be e to the 4x times 4x minus 1 all over x squared. Again, that factoring to clean things up is a really useful thing to just get in the habit of doing, because when you need to do it, it's super helpful. Whether that's finding extrema or that's taking second derivatives or what have you. Here's y equals x over e to the 4x. With the same situation, I'll use the quotient rule. So this is 1 times e to the 4x minus x times 4e to the 4x all over e to the 4x squared. I'll clean up the numerator by factoring out e to the 4x, and I'll be left with 1 minus 4x. The denominator, I'm going to leave it as e to the 4x quantity squared, although I could do power to a power and write that as e to the 8x. And the reason I'm doing that is because one of the e to the 4x's will divide out. This is 1 minus 4x over e to the 4x. Another example involving derivatives. If we have y equals the cube root of e to the x, recall that this is the same thing as e to the x all to the 1/3 power, and this is not power to a power. It would be power to a power if it was x to the 1/3, and it isn't that. But we can use the power rule and some chain rule here. So this will become 1/3 times e to the x to the negative 2/3 times the derivative of the inside, which is e to the x. And when I multiply e to the x to the negative 2/3 times e to the x, this ends up becoming 1/3 e to the x to the 1/3. So there are quite a number of derivatives. In part 2, we'll consider implicit differentiation, second derivatives, and some other kinds of problems. And then in part 3, we will look at integrating involving these things.